Hello viewers, welcome to Resonant, taking you through the story of A-level physics paper 2. And this video we are going to go through the topic of magnetism and alternating current. So in particular, we are going to look at the calculations involving alternating current for resistors, inductors and capacitors arranged in series. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So these are the subtopics under the topic of magnetism and alternating current. What is ticked means it's already available on the platform, and what is not yet ticked means will be uploaded with time. So in this video we are going to go through the subtopic of resistors, inductors and capacitors arranged in series and connected to an AC source. So in these videos we are interested in the calculation bit of it, but complete notes are available in the books I recommend. So in physics there are 4 books. So there is Physics Paper 1, Physics Paper 2, Topical Question Bank and its solutions. In mathematics there are also 4 books: Principal Mathematics, Math Paper 1, Math Paper 2, Termly past papers with marking guides and a topical question bank. In subsidiary mathematics there is only 1 book with both notes and past papers. So for any of the copies, contact the author on this contact. So we have resistors, inductors and capacitors, where you are going to look at bit by bit. For example, so this video will be broken down into 3 parts. The first part will be series arrangement of resistors and inductors. The next will be series arrangement of resistors and capacitors. And the last one will be series arrangement of resistors, inductors and capacitors. In the previous video we looked at individual arrangement of resistors, capacitors and inductors in series with an alternating source or alternating voltage. But now we are going to look at combinations of first beginning by two components, and at the end we shall look at all the 3 components arranged in series. So that is a resistor. So this is the alternating voltage, pure resistor, and this is a pure inductor connected in series with an AC source. So here there will be voltage across this resistor and also voltage across the inductor. So when you add the 2, you come up with the voltage of the source. So when we know the current, it means that voltage PD across the resistor will be IR. If we know the inductive reactance of this inductor, then PD across the inductor will be I times XL, where XL is the inductive reactance. Then the total voltage will be IZ. Now this is a new word we didn't see in the previous video. So each time you combine more than one component, so maybe a resistor and an inductor, or a resistor and a capacitor, or all of them, what we get as the total, we would call it resistance, but okay, a combination of resistance and reactance gives you what we call impedance. But let us see how to define it. So by definition, impedance is the resultant opposition to the flow of alternating current in a closed circuit containing reactive and resistive components. So I think you remember in the previous video we saw that inductors and capacitors are reactive. They only have reactance, they don't have resistance. It's only a resistor which has resistance. So when you combine reactance and resistance, we come up with what we call impedance. So phasor diagram for the above circuit. I think remember in the previous video we saw that for a pure resistor, both current and voltage are in phase with each other, meaning that the angle between current and voltage is 0. But when it comes to a pure inductor, it was voltage which was leading current, meaning that the voltage is here and current will be here, like that. So when you draw a phasor diagram for this combination of the two, when they are connected in series, it means that both the PD for the resistor and the current will be in phase. That's why there is 0 phase difference. But the PD for an inductor leads the current by 90. That's why here it is ahead by 90 degrees. So we saw those phasor diagrams in the previous video. So if you have not yet watched the previous video, I encourage you to first watch it before you come to this, because this is a continuation. So after that, we can now get the resultant of these two, and that will be called the total PD, or PD of the source. So theta is what we call the phase angle. So from the phase diagram and by Kirchhoff's law, we realize that the resultant will be got by Pythagoras theory, where it will be V squared will be equal to VR squared plus VL squared. So in direct current electricity, the calculations are a little different for getting the total PD, because in direct current we just say that V total is equal to V1 plus V2. But when it comes to alternating current, we use phasor diagram. When we come to alternating current, we use phasor diagram to get the total current when it is in parallel, and also total PD if it is in series arrangement. So when I substitute for V, remember in the previous video we saw that V is IZ, VR is IR, and VL is IXL. So there I realize that I is common, so I can pull it out, I can cancel it out to remain with this. Therefore, when I make Z the subject, that is what we call impedance. So impedance, or a combination of resistance and reactance, is got from Pythagoras theory. So alternating current, the calculations a little differ from the ones of direct current. Here we use phasor diagram. So from this diagram still, V tan theta is equal to opposite over adjacent. That's why you see a tan theta is equal to VL over VR. And VL we saw that is IXL, VR is IR. So when R cancels, we remain with XL over R. That is inductive reactance over resistance. So those are the two calculations when it comes to series arrangement. One is impedance, the other one is phase angle. This is called phase angle. So we already know from the previous video that XL is equal to omega L, so I can substitute and come up with this expression. It is still okay. So with that, shall go through the calculations. Question 1 says a 30 ohm resistor and a 0.2 Henry inductor are connected in series. See, this is the keyword series, to a 50 Hz AC source. Calculate the total impedance of the circuit. So 1XL we saw that is equal to 2 pi FL. So substitute for frequency, inductance to come up with the inductive reactance. Then from there you can come up with the impedance, which is equal to square root of R squared plus XL squared, to give you this as the impedance which they wanted. Question 2, a resistor with a resistance 20 ohms and an inductor with inductance 0.3 Henry are connected in series to a 230 volt 50 Hz AC source. Calculate the current flowing through the circuit. So here still we'll do the same. First get the inductive reactance but from 2 pi FL, then get the impedance from square root of r squared plus xl squared to give you this. Then after that, I can remember that total PD is equal to IZ. So I will be equal to V over Z, which is V is here, impedance is here to give you the current they want. Question 3. A 4 ohm resistor and a 0.3 Henry inductor are connected in series to a 120 volt 60 Hz AC supply. Calculate the voltage across each component. So we know that inductive reactance is 2 pi FL, which gives this. Then impedance square root of R squared plus XL squared to give you this. Therefore, total current, this is now total current, will be equal to V over Z, which is V here, Z is here to give you this. Therefore, now that I know total current, I can get the PD across each. So PD across the resistor is IR to give you this, and PD across the inductor is IXL. So here there are two ways you can either use that, because we know that total PD is equal to the sum of these two. Or another one can say VL is equal to IXL, it is still okay. Question 4. A 50 ohm resistor and a 0.15 Henry inductor are connected in series to a 110 volt 60 Hz AC supply. Calculate the power dissipated in the resistor. So one inductive reactance is given by 2 pi FL, which is that. Then impedance is square root of R squared plus XL squared to give you this. Total current is V of total PD over Z to give you this. But they want power, so I can come and say that power is I squared R. So I squared R, where this is this and this is that. Now this one may confuse you, but what you should know is that in this calculation, like I told you in the previous video, the values given are in RMS. So here, this PD they gave is an RMS value. That is why you're just using I squared R, because if this was not a peak value, we would have used half I naught squared R. I think you remember that. We saw two formulas. We saw the one where you are using peak current, and another where you're using RMS value. So here, if they just give a value here, just know that it's an RMS value. That's why I'm not using a half I naught R squared R. We're just using I squared R, because this current is a root mean square current. Question 5 says a 25 ohm resistor and a 0.05 Henry inductor are connected in series to a 100 volt 50 Hz AC source. Calculate the phase angle between the voltage and the current. So remember, phase angle, we get it from tan theta equal to XL over R. So I need to first get XL from 2 pi FL, which gives you this. R, I already know it, so I can come and quote tan theta is equal to XL over R. Then substitute for XL and for R to get the value of theta. And that would be the phase angle they wanted. Question 6 says a pure inductor of 2 Henry is connected in series with a 500 ohm resistor across AC mains having a frequency of 50 Hz. Okay. A high resistive voltmeter connected across the mains reads this, so that's an RMS value. Determine its reading when connected across the resistor. In other words, the one they PD across the resistor. Then 2 when connected across the inductor. They're the one they PD across the inductor, and 2 and 3. Why is the sum of the values in Roman 1 and Roman 2 not equal to 240 volts? The reason is because it's an alternating current, and I think, like I told you, okay, we shall see it. We shall see it when you reach there. Let's begin. Let's go slow. Roman 1. Roman 1, we know that We know the inductance is this, so I can get inductive reactance. My aim is to first get the total current. So after getting inductive reactance, I can get impedance from square root of R squared plus XL squared, which gives you this. Therefore, from impedance, I can get the total current, which is that. And therefore, now I can get VR from IR, and also I can also get VL from IXL. Then Roman 3, why the sum is not the same? Because I think realize that when you add this and this, you don't get 240. The reason is because this gives you this. Okay, this is this which is greater than this. Okay, but why? So that voltage across alternating current circuits are vector quantities that have a phase difference of up to 180 degrees. So that is why I told you that here we use phasor diagram to obtain the resultant, to obtain the total PD or total current. You don't just add as it is the case in direct current. Okay, so now we shall go to a case, the next part, where we now connect resistor and induct and capacitor in series. So we have a resistor and we have a capacitor connected in series. So that means that voltage across the resistor is IR and voltage across the capacitor is I.e.c., where Xc is the capacitive reactance, and total voltage is Iz, where Z is the impedance. I believe by now you know what an impedance is. So phasor diagram, like I told you, to get the resultant, you need to know the phasor diagram. In the previous video, we saw that a pure inductor, both current and voltage are in phase. But when it comes to a pure capacitor, it is current which leads voltage. I want to know the difference, because we have three components. One was a resistor where both current and voltage are in phase. Then we have an inductor where it was voltage leading current. So here there was voltage, here there was current, and it was leading current by 90 degrees. Okay, now when we come to a capacitor, we saw that it is this time current leading voltage. So meaning that here there is current and here there is voltage. Okay, like that. So if you want, that means that if I want to maintain current to be on the horizontal, it means that my diagram will be rotated a little like this. So when I rotate, it means that when current is here, okay, voltage will be this side. So that still it is current leading voltage, like that. So when we draw a phasor diagram, we shall come up with voltage and current for a resistor in phase. But when it comes to voltage of a capacitor, it is lagging behind current. So it will be behind by 90 degrees. Then you can get the resultant PD from Pythagoras theory, where V is equal to V squared is equal to VR squared plus VC squared. Then come and substitute for V, VR and VC, then cancel out the current to come up with this, make Z the subject. So it's somewhat similar to the previous one, only that here there was inductive reactance and now we have capacitive reactance. Same applies to the phase angle. Here it was inductive reactance, now we have put their capacitive reactance. But the rest is the same. So with that, we can go through some of the calculations. Still, the format is the same as the previous ones, but we have to do some for that so that we get well versed with the difference between RL circuits and RC series circuits. So question 1 says a 50 ohm resistor and a 10 microfarad capacitor are connected in series to a 60 Hz AC source. Calculate the total impedance of the circuit. I think you also remember question 1 for RL circuit was also asking about total impedance. So the format is the same. The format is the same. So still we shall do the same. We first get the capacitive reactance, which is this. Then we can get the impedance from this expression. Question 2. A resistor of resistance 40 ohms and a capacitor with a capacitance of 2 microfarad are connected in series with a 230 volt 60 Hz AC source. Calculate the current flowing through the circuit. So you come and first get capacitive reactance. So this one is in microfarad, you convert to SI unit to come up with this as the capacitive reactance. Then you can get the impedance. After impedance, we can now get the total current, and that's what they want, because series current flowing through both components is the same. Then question 3 says a 20 ohm resistor and a 15 microfarad capacitor are connected in series to a 110 volt 50 Hz AC supply. Calculate the voltage across each component. So we shall first get the capacitive reactance. After that we can get the impedance. Then from impedance we first get the total current. And after the total current, you can now get the PD across the resistor, and then lastly PD across the capacitor. So I think you realize the specifications are somewhat similar to the ones of RL circuit. By this time, what you have done, you have replaced the inductor with a capacitor. Then question 4 says a 30 ohm resistor and a 5 microfarad capacitor are connected in series to a 120 volt 50 Hz AC supply. Calculate the power dissipated in the resistor. So still shall first get current, but before we get current, you need to get capacitive reactance, which will be used to get the impedance. After impedance, we can now get current, which is V over Z, and from current, we can now calculate the power dissipated, which is I squared R. Then question 5. A 25 ohm resistor and an 8 microfarad capacitor are connected in series to a 100 volt 60 Hz AC source. Calculate the phase angle between the voltage and the current. So if you do the same, first get the capacitive reactance, then you remember that because you now have capacitive reactance and you have the resistance, meaning that you can get the phase angle from tan theta equal to xc over r. Substitute for xc and for r, then make theta the subject. And that's what they wanted. Then question 6 came from U.A.C.E 2024, which is last year. Paper 2, question 7c, and it says a capacitor of 20 microfarad is connected in series with a resistor of 100 ohms across an AC source of frequency 30 Hz and peak voltage 60 Hz. Determine the root mean square value of the current that flows. So here we have the capacitance, we have the resistance, we have the frequency, and we have the peak. Now here they have specified, that's what I've told you. When they don't specify, it is an RMS value. But here they have told us peak voltage. So a capacitive reactance is 1 over 2 pi FC, which gives this. Then impedance is equal to square root of R squared plus XC squared, which gives this. Remember, they want the RMS value of current. So that means that when I have this, I can still get the peak current from V0 over Z, which is that. Then after getting the peak current, I remember the relationship between peak value and RMS value. Substitute and get the answer they want. Question 7 says a circuit consists of a capacitor of 2 microfarad and a resistor of 1200 ohm. An alternating EMF 12 volt RMS and frequency 50 Hz is applied. Find Roman 1 the impedance of the circuit, Roman 2 the current flowing through the circuit, Roman 3 the voltage across the capacitor, Roman 4 the phase angle between the applied EMF and the current, then Roman 5 power supplied, and Roman 6 average power dissipated. So average means we are now using peak value. So 1 capacitor reactance is 1 over 2 pi FC, which gives you this. Therefore impedance with the S is equal to this. Roman 2 current will be equal to V over Z, which gives you that. And Roman 3 PD across the capacitor is e.t.c, which gives that. Roman 4 phase angle, if you get it from tan theta is equal to xc over r, substitute for xc and for r to get the value of theta. Roman 5 power supplied is IV, which is equal to this. Then Roman 6 power dissipated is I squared r. Now here, this current here, let's see here, the current should be RMS. Let me see. If we look at here, yeah, it is true, because here the PD was RMS, meaning that if I use PD to get current, it means that this in the current will be RMS. That is true. That is why they used I squared r. If it was peak value, it would have been a half I naught squared r. So note the difference. You can get power dissipated using RMS value, or you can also get power dissipated using peak value. We saw all those scenarios in the previous video. Alternatively, power dissipated can be IV cos theta, where I come up with this, where theta is the phase angle. So now shall go to a combination of all the three components: a resistor, an inductor, and a capacitor. That's the capacitor, then the inductor. So same current flows through all the three. Then for the phasor diagram, remember we said for an inductor, it was current which leads voltage. Okay, now let's do this. For an inductor, if current is here, voltage will be here. So this will be VL. Okay. When it comes to a capacitor, when current is here, voltage should be down, because it is current which leads voltage when it comes to a capacitor. So when I combine this with this, I'll come up with something like this, where that is the VL and this is the VC. So if VL, we take VL to be bigger than VC, then the resultant, because remember this is in a straight line, so resultant will now be taken to be VL minus VC and in an upward direction. So we can redraw this to come up with something like this, where I have that, and that. So in this case now it becomes easier to get the resultant of these three PDs. So theta is the phase angle. So here I can now say V squared is equal to this squared plus this squared, like that. So that's what I was meaning. Then you can substitute for V, for VR, VL, Vx. Then I can realize that I can cancel to remain with this. Then make Z the subject, that will be the impedance. So from the phasor diagram, still tan theta will be equal to this over this. But remember that VL is this, VC is this, VR is this. So when I cancel out I remain with this as the value which can be used to get the phase angle. So with those formulas, we can now go through these questions. So in short, questions on RLC circuits in series are always on impedance, phase angle, and power dissipated. So question 1 says a 40 ohm resistor, a 20 microfarad capacitor, and a 0.1 Henry inductor are connected in series to a 50 Hz AC source. Calculate the total impedance. So yeah, the first thing to do is to get the inductive reactance and also the capacitive reactance. After that, we remember the formula for impedance, which is equal to R squared plus bracket of XL minus XC. So R squared, XL, XC. Everything gives you that. And that's what they wanted. Then question 2 says a resistor with a resistance of 50 ohm, a capacitor with a capacitance of 5 microfarad, and an inductor with an inductance of 0.3 Henry are connected in series to a 230 volt 50 Hz AC source. So that means that this is an RMS value. Calculate the current flowing through this circuit. So XL inductive reactance given by that, capacitive reactance given by that. So we have to first get the total impedance, then after which you can get now the current. So impedance will be given by that. Use the calculator to come up with this value. So now I have impedance and I know the total voltage. I can now get the current from V over Z, which gives me that, and that's what they wanted. Question 3 says a 30 ohm resistor, a 10 microfarad capacitor, and a 0.2 Henry inductor are connected in series to a 120 volt 60 Hz AC supply. Calculate the voltage across each component. So to get the voltage, you need to first get the total current, but before you get total current, you need inductive reactance and also capacitive reactance. Then after that, I can now get the impedance. Then from impedance, I can now get the total current. And this current can be used to get the voltages. So PD across the resistor will be IR, which is that. PD across the inductor will be IXL, and in the capacitor will be IXC. And that's what they wanted. Question 4 says a 25 ohm resistor, a 15 microfarad capacitor, and a 0.05 Henry inductor are connected in series to a 110 volt 60 Hz AC supply. Calculate the power dissipated in the resistor. So you'll need inductive reactance, capacitive reactance, and those will be used to get the impedance. From impedance, I can now get the current, total current. After total current, I can now get the power from I squared R, because this value is an RMS value. Question 5. A 20 ohm resistor and an 8 microfarad capacitor and a 0.1 Henry inductor are connected in series to a 100 volt 50 Hz AC source. Calculate the phase angle between the voltage and the current. So shall come and say that XL is that, XC is that, then the phase angle can be got from tan theta is equal to XL minus C over R. So here, this thing, this gives a negative, meaning that phase angle would be negative. Negative meaning that would be in the opposite direction, because previously it was up, isn't it? It was like this, current was here. Here was VL minus VC. Therefore, the angle was above the horizontal. So now that it's negative, it means that it was the other way around, whereby PD across the capacitor was bigger than PD across the inductor. So now we shall go to a term called resonant frequency. This is covered more in waves. Resonance is covered more in waves, topic of waves, but also here we need to know something about it, about resonance frequency. So resonant frequency is defined as the frequency at which current becomes maximum and impedance becomes minimum. So from algebra, we know that for this expression to be minimum, it implies that this term should be 0. And when it is 0, we shall come up with XL being equal to XC. Now what is XL? Is omega L. And X is what? Is 1 over omega C. So when I rearrange, make omega the subject, take omega this side, you come up with omega squared equal to 1 over LC. Make omega the subject, I'll come up with 1 over square root of LC. That means that from omega equal to this, when I substitute, I'll come up with, substitute for omega to come up with 2 pi f naught. Now this f naught is what we call the resonant frequency. So make it the subject, so this will be the formula for resonant frequency. 1 over 2 pi square root LC. So with that, we can go through this question. Question 1 came from U.A.C.E 2019, paper 2, question 7E, and it says, a lamp of resistance 10 ohms, a capacitor of capacitance 0.4 microfarad, and an inductor of inductance 0.4 Henry are connected in series to an alternating voltage source of 0.01 volt RMS. The frequency F is varied from low to high value while maintaining the amplitude of the applied voltage constant. Roman 1, calculate the resonant frequency, and Roman 2, find the voltage across the capacitor. So here we shall come as that resonant frequency is 1 over 2 pi square root LC, which gives you that as the resonant frequency. Then the voltage across the capacitor, we shall need to first get the impedance. Remember, impedance in this case, it is equal to resistance because the other term was 0. The other term of XL minus XC was equal to 0. So remain with Z being equal to R. Therefore, V equal to IZ, we will come up with this, meaning that I is equal to 0.01 ampere. Therefore, for the capacitor, this is equal to IXC, which gives this, and in the end, we come up with this. So that brings us to the end of this video. Thank you for watching, and be reminded that